Welcome back to the Valve Studio. This afternoon I'm working on my lunchbox amplifier, particularly the output stage. And remember, we're going to try to power our amplifier and use only these Pentodes. This is a 6SJ7, both for the preamp and for the output stage. And I did a previous video where I kind of determined that this is capable of putting out almost a watt of power at 230 volts. The 230 volts comes from the DC to DC power supply that we've previously also covered that runs on an 18 volt cordless drill battery. So this video is a little bit different than normal. Normally I figure out what I want to cover, I shoot all the segments, I edit everything together. This one I just actually turned the camera on, so you're going to get to see the design process that I went through to determine if this is going to work. Now I'm using this tube, a 4x6 4 ohm speaker, and the output transformer that's used to drive a reverb tank. And so because there's no script involved, I'm kind of rambling on. There's a few verbal mistakes in the video, but you basically kind of see the process that I went through to determine that yes, it is possible, and we do get out probably about 0.8 watts out of this tube running at 230 volts. So let's go ahead and get started. Alright, here's our output transformer. This is been used in for reverb driver. And we're going to first look at this. So I can go get the data sheet for this, but we'll just figure out which one of these pairs is the primary and secondary. So I'm going to use this LCR meter that I bought. It's a RuoShui 4091C, and I bought this particular one because it has a frequency resolution of 1 hertz. So I can go from, I think it's probably 10 hertz to 100 kilohertz at 1 hertz resolution. So in order for us to figure out, we know this output transformer, we're going to determine, we can look at just the DC resistance of the primary and secondary coils, and the one with the lower resistance is the one that's meant to drive the speaker, which is the secondary. So this, I'm on DC resistance now, so this pair over here is 1 ohm. And the next one, and you can do this with a regular handheld digital multimeter as well. This isn't going to tell us a turns ratio. All we're going to do is tell us which one of these is primary and secondary. And this is the primary here. All right. Okay, this guy over here is potential for our speaker for our lunchbox amplifier. This is a 4x6 speaker for a car, and let's measure its DC resistance right now, since we're still on DC resistance. Its DC resistance is 3.6, but you don't run things at DC, so what we can do with this is let's measure the impedance of this at mid-band, which on this speaker here would be about 1 kilohertz. So we'll come back over here and we'll click this back to here, and we can right now it's on 1 kilohertz right now, and it's 4 ohms. Okay, so this is a 4 ohm speaker, so go ahead and label that. Find my Sharpie here. Okay, that's good. So we don't know the turns ratio of this yet. That's really not important. What is important though is that when we couple these two together, what is the impedance seen by the primary? So let's go in here and connect this guy up. And I think this one fits over here a little bit, and this one's over here, and that's kind of loose. No, that's fine. Alright, so put this over here. And connect up our LCR meter. We're going to measure the impedance of the primary. Not let them touch. Okay, our impedance of the primary is at 15K. So that is what the plate of our SJ7 amplifier is going to see. So we'll write that down. Find me a pencil here. Write this down over here. 15.6 K. And this is a Z. This is an impedance because you can see that there is a phase angle associated with it. All right. So next is I'm going to show you this little thing. So this is a product that I'm considering selling. This is a prototype. This is for a project I call TAC, which stands for Tube Amplifier Construction Kit, and they have these little boards. And let me see if I have another one of these over here somewhere. So this particular one is for a footprint of an 8N. An 8N is a pentode, a true pentode, not a beam tetrode. And its footprint, really, the most common tubes that are used for this is SJ7, which is what we're using, AC7, SK7. So those are pentodes there. Let me see. Here's one that I'm trying out for this footprint is for a 9A, which is a dual triode, which is for 12X AX7. You can kind of see. And why I'm doing this is that it's quite tedious. There's a lot of overhead if you want to get your soldering iron out and want to try a lot of different things. And so I came up with this idea here. These are push terminals, and we'll just go ahead and use this today. And at some point I'm going to start selling these, and there's about, I believe there's 9 different versions of this for different footprints and different scenarios that you want to use them in. We'll make a video about this more in the future, but for today we're just going to use this. So let's go ahead, and our target pentode is this one here. This is the, what is this one? Oh, I'll focus on that one. 6SJ7. All right. First thing we're going to want to hook up is the heaters or the filaments. And then down here I have my regulated high voltage power supply. This is a what is this? A Heath SP-17A. This gives me both 6.3 and 12.6 filament power. It has 2 outputs powers. It's got a minus supply. The minus supply is for biasing, and the plus supply over here, this is B+. This goes from 0 to 400 at 100 milliamps. And this one will go from 0 to minus 100 volts at 1 milliamp. And I can draw 4 amps out of the 6.3 filament output. So what we're going to do is we've got a little screwdriver. We're going to press down these little tabs here. And all right, good. Now we're done. And these guys are in there good. They're not going to come out. These guys will accommodate easily 18 gauge wire, as well as those 5 watt resistors that you might need to use for your cathode biasing. Okay, first of all, let me just go look in here. Excuse me. There is a little footprint here, but it's not very high resolution. So here's our footprint we're working with. Now this is a true pentode and it doesn't connect up the suppressor grid. So we got to go from 3 down to 5. So we got to run a wire from 3 to 5. So a little piece of wire here. Now this is not labeled. This board's not labeled. It is labeled the pin numbers here from the top side. Now, and this is showing you the bottom side pinout, so everything's flipped around. But this one's really labeled with the labels. So we have grid, screen, plate, cathode, and we have two cathodes down here. But we need to run a wire from the suppressor to the cathode, so we got to run down from here down to here. And this is getting warm. Yeah, this is starting to warm up a little bit, which is good. All right, so that's not coming out. And our speaker, needs to go from the plate. This is meant for the high voltage connection. If you look at this schematic, these are 2-layer boards here. The board layout only has these 3 connected together. I don't have any high voltage on this yet, so I'm not too concerned. So what we're going to do is, this is typically, if you're making this as a preamp tube, you put a resistor in here, you put your load resistor in here, but for us, we're going to put our speaker in with the primary. So we're going to go ahead and cut these fast connects off. And that tube is getting even warmer. Maybe I should turn off my power supply while I get this wired up. Let's do that. If you're wondering what tools I use for this stuff here, I always use these things here. These are Klein 1146 strippers. These are the ones that don't nick the wires. Okay, these are good. These are great. All my toolboxes have these. And I'm also using one of these things. This is a Jokari. What is this one? I don't know. 250. This is an automatic stripper. This is kind of handy, and it does a good job at not nicking the wires either, and it strips a lot of different gauges. So for us today, we're just going to go fast. So we have our primary and secondary winding. We're going to connect it across here. Oh, and I'll show you one more thing about this. Let me just show you a few more of these boards here while I got them out here, just to give you a little teaser. Okay, on the bottom there's some feet. Okay, and those feet are meant to go in the pegboard. So what you see here is I think this is a 16 by 16 pegboard, and all these little boards here are meant to go into this pegboard and snap into this pegboard so your parts don't move around. And then typically what you're going to do is you're going to get, let me see here, so let's say you're going to use, here's this is one for a footprint of an 8BD. These lock in there like that. This one here is for this is a 5T rectifier tube. Let's move this out of the way. This one's 5T rectifier tube. So you can make your complete power supply on this one. And this one can lock into those foots as well. So nothing moves around. So it's pretty secure from a high voltage perspective. You don't want this stuff kind of moving around a lot. I'm not using this today because I'm only working with one tube. But that's what these are designed for. They're all made with these 3D printed little feet that just kind of lock right into the footprint that's 1 inch spacing. Okay. All right. Back to today's video. Let's throw these things away. All right. I should probably turn off my phone, but Hopefully no one will call me. It is a Sunday, by the way. Alright, so we got our primary and secondary hooked up. So now we got to run wires up from down from our high voltage power supply down to here. So we're going to run directly from the cathode up to this point here in our circuit. So I need a twisted pair. So we will pick up, what voltage should we use for a twisted pair? I guess we use a red and black. So here's our red and black wires. We'll get a nice big piece of these. Okay. I'll show you how I do this here. So I have this is a 1/4 inch. This is the chuck for like a Dremel tool, and I put it into my little drill here. And in order to twist these together, you've probably seen this, or you probably do it yourself. Just use a regular drill, but I don't have a drill here. But I almost always have this little DeWalt screwdriver, powered screwdriver here. So we'll connect these guys up, screw those into there. And then on the other side, I'm going to grab it with these channel locks. Now I'm going to be off camera, so you're not going to see this, but you kind of get the gist. Going to connect up to the cathode. We're going to do fixed bias on our test circuit this afternoon, instead of self-biasing, which is use a cathode resistor. We can do a cathode resistor, but we're not going to use it today. That's why this extra one is down here. There's an extra one that's uncommitted. All three of these are connected together. But if you wanted to use this this board and do cathode biasing, or you could put a resistor between here and here, and then you'd connect your high voltage down here, and then this would be the voltage that's developed across your cathode bias resistor. But today we're going to do fixed biasing, which is where we put a DC voltage on the grid. Now we could turn it on now, but now it's just going to act like a diode, and our current's going to start to flow, and we're not going to be able to control the current, so we don't want to really do that just yet. We want to wire up our bias voltage as well. So for our bias voltage, we will choose another wire pair. We'll have black again. And we don't actually need to run 2 wires down to here, because we can make a ground connection right here on the power supply to connect my two power supplies together, my high voltage and my bias voltage together up there. So I'm just gonna connect these two together up here, which is good. And we need our bias voltage coming down, and we will pick for that. The color is orange. Voltage, and we want to connect up to the grid over here. We are going to need one more voltage. Okay, that's connected in there. And our minus is over here. Okay, so with both voltages, both knobs turned down, I think we can turn this on. And you'll see that we got we're starting to get a little bit of DC voltage out over here. Get that back over there. There we go. Duh. Okay. The this circuit that's in this actually uses I think it's a 6L6 for the bypass element, or maybe two 6L6s or 6V6s for the bypass element in the regulated power supply, which is the device that has to dissipate all the power dissipation. So they use a vacuum tube for that. All right, there's one more. Let's turn this down. Well, we're turning up the bias, so we're applying actually really negative voltage to this, to the grid, so that no currents are really going to flow through the plate. All right, there's we need to be able to measure that current through the plate, but we'll do that in here in a little bit. We can do that. Actually, we can do that on using the instrument up above. Do that for today. So let's. All right. Let's. For now, we're going to connect a screen right up to the high voltage power supply. So remember this little circuit that we had, that little DC to DC switching. Oh, was it this one? I think it was. No, it's not that one. A couple of videos ago, I looked at using one of these things. These are one of these things to run Nixie tubes, and I believe that I've found that the 15-watt version of this is going to work better than this 20-watt version. And these guys got up to about 230 volts. So with that, for today, we're going to connect the screen up to the high voltage power supply and run our this voltage up here, our main power supply, at 230 volts. So let's go ahead and put a connection wire here. Now in our final design, we may end up actually biasing this down a little bit, but for today we're just gonna play around a little bit. Turn this thing on. Okay, so over here we're running minus 20 volts into here. Let's look at the tube characteristic for just a second. So this is a tube characteristic for a 6SJ7, and this is, if you're running the screen at 100 volts, we're running a screen much higher than that. But what we're really looking for is what's the range of the swing that needs to be on the grid. So this negative voltage down here is -7. Now when we make it a little bit bigger, we're gonna expand this up. This one might go up to -10, but what we're really doing now is we're running this tube way into cutoff down here, because we're cutting off this tube. So because I have -20 on there now, so we're like, we're way down here, which is fine. So if we were to turn up the high voltage now, we really should see no current draw in the plate circuit. So we will come over here and click our meter back over. This is milliamps and this is volts. So what we're going to do is turn up the high voltage on the plate circuit up to about 230 volts, which is going to be about there. And you can see that there's no plate current. Now this range goes, oh, it's kind of goofy. Oh, this range goes from up to 100 milliamps is what it goes. So they have kind of the wrong scale here, but there's a little arrow right there, and that 2/3 of that's 100 milliamps. So if we turn this knob down, you will see that this current will start to go up. Okay, so now it's going up. Okay, now we don't want to have it go up too far because we need to make sure that we don't violate the wattage dissipation in these guys here. Let me get this out of the way. Get too much junk in here today. All right, let's go back over to here. So the wattage dissipation, I just don't have enough room in my camera view today. Screen dissipation is 0.7 watts. Plate dissipation is 2.5 watts. So I need to make sure we don't exceed that because I don't want to blow up my tube today. But if we were to bias up some stuff here, I believe we can take some measurements. So what we want to do is we are going to want to with the hold on, I will be right back. I'm going to print something out here. Just hold on. Okay, let's move some of this stuff out of the way so we can talk about something for a minute. So this is from my Pentode Class A1, Class A1 designer. I just printed this out. So what we got here is I've set up my plate, my screen voltage. I've put my load impedance in at 15.5 kilo ohms. And so what this is kind of recommending for me, this is 15.5, so this is the actual load that the Pentode plate is actually seeing. So that's this middle line. And if we look down here, if we're running at 230 volts, in order to avoid the power dissipation curve, we need to be running right up around here. So this voltage is going to be, I believe, shoot, I don't even remember. Do I do? Are these half volts? Half? Oh, crap. Well, if it's not, we'll find out. So this one's 0, 1, 2, 3, 4, 5, 6, about 7 volts down is where we should be. And if we're down at this point, we should be at about 10 milliamps and still be below this curve here. So let's turn the voltage down to 7 while we're watching this and see if we can get this up to 10. Once we get to 7 is the current drive at 10. So let's move these things back in here. Now what's cool about all this is I'm moving this stuff around and I'm not really too concerned about getting shocked, because everything's secure and there's no exposed wires. There are on the bottom of the board, but I'm not getting anywhere near the bottom of the board. So let's go back up to our meters up here. We're going to turn this down. Actually, I think we need to put our jumper back in there. We're going to turn our bias voltage down while we're monitoring the milliamps and see if we can get that to go up to 10. You see it's kind of rising. 10 is about there. So what we want to see is what is the bias voltage when we did that. And our bias voltage is 7.3 volts. Ho-ho! Would you look at that? This thing actually predicted where we should be. All right. So we want to, now we need to couple this is something that we're going to have to do. We have to figure out, move this out of the way again. So in order for us to go across this extreme of swing, we need to go from here, which is 0 volts, down to this line down here. So we need to swing 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13, 14, about 15 volts in order to get this whole swing. Now, unfortunately, I don't have I don't have a signal generator to kick out that much voltage. I do have one that will kick out what does it kick out? It kicks out about 13 volts. So if we're going to put a signal on here, and we're going to at 1 kilohertz, and we're going to start turning it up, and we'll take a look at what happens with our circuit there. And we're going to couple it through a, wow, that tube's getting pretty warm. We're going to couple it through a capacitor. And what I got here is a, what is this guy? See if you can see that. 1 microfarad capacitor. Just going to connect it up to the grid. And we're going to clip our wires on. Is that in there? Yep, that's in there. And we need a wire in this little side of the circuit over here. You can see that this is the signal going in. This thing running now. Yeah, this is running. Let me make sure we got this going right. Yeah, it's going on. Got to turn down that amplitude a lot, because that amplitude was, yeah, it's getting up there. Gonna kind of couple up a thing here and see if we get, yikes, that is getting warm. That was getting really warm. Let's try to do this without burning ourselves this time. Get in there. Okay. Now we got A, B, and C. And in here, and I need a adapter for that. Need one of these guys. Got our amplitude down. Going to couple in our sine wave. But you can see that we're getting a little noise spike. Let's move this over here a little bit so you can see what I'm doing. Got to couple in over here. And we're going to turn up our amplitude on the input circuit. That's pretty good. So let's take some measurements here. You can hear me. Let me turn this off a minute. Okay. Oh, how can we do this? We want to measure the, we're going to measure the voltage swing driving the speaker. Let's see if I can get this wired up. I'm going to bring in another voltmeter here. I, like you, probably have too much stuff on your bench. So much stuff here. I have low voltage power supplies, high voltage power supplies, ESP32s, displays, speakers, CNC drivers. Get involved in a lot of different projects. All right, what's next here? Remember, we know that this is a 4 ohm speaker. So if we're going to come down here and connect up our I think I can get this guy to clip on there. And we want to be over on volts. I'm going to turn this up. Connect this back up again. That's a 1/2 volt. Alright, so it was 1.8 volts. I'm getting my calculator. .8 volts. Let's see if I can get this in here. Certainly don't want to blow this guy up. Let's keep this guy out of here. This is my vintage HP41C that I got for high school graduation. So we have 1.8 squared, V squared over R, and R is 4. So you can't see this because it's out of focus, but 0.8 watts, which is really close to what we're expecting. But we are getting some distortion. This tool over here predicts our voltage, our wattage to be 1.1 watts. And I don't think we're getting this entire swing of this load line. But we are getting some distortion, audible distortion. So let's take a look at that on the scope. This is where I need to be a little more careful, because I have to connect the scope probe up to the high voltage. So we're going to have an exposed wire when we do this. We would like to not do that, but we're stuck. We're stuck doing that. So here, let me get my pointer out here. Okay, so we're going to connect our scope ground to this wire here, because this is a ground coming out of the power supply, and we need to connect the scope probe up to the plate itself. So this guy here, let's measure what that voltage is running at. Now these things here, you can also just put your scope probe into these holes and measure voltages right on these holes. This is 223 volts right now. And you see, that's pretty nice. I mean, you can put your meter probes right in these holes and touch things without having to worry about them falling off like they would if you had soldered things together. So these boards are really handy. And I've had them for a while. I just have not had the time to put together a way to sell them. I know I could use Tindy for that, but I would like to sell them off my own website using one of the credit card vendors. And a friend of mine has got a product he's trying to do that with as well. So I'm trying to get him to figure it out. What is that one that I was going to use for that? Whatever. I'm rambling now. All right, I'm going to turn off the high voltage for now, so that we can make sure that we're not wiring things up to a high voltage circuit. This voltage now is off. Okay. I'm going to connect this up here. This is the wire here that you want to be careful of. So I'm going to connect my scope probe to this. come over to this guy here. All right, so we're all connected up. We'll turn our high voltage back on. Get this out of the way. All right, let's just let us review before we turn it back on. Signals coming in here. Capacitive, we couple it over to the grid. We've got the grid bias down to minus 7 volts, so that we're actually on the predicted load line, which is right here. We're underneath the power dissipation curve, so we won't have any problems with potentially destroying the plate or the grid in our tube. We looked at the wattage output. We're at 0.8 watts. So now we've got a scope probe connected up to the plate and down here to the grid, which is ultimately the ground in our circuit is this cathode down here, not to the grid. The cathode in our circuit is actually the ground point in our circuit. We're going to look at the waveform coming in here, and we turn the high voltage back on. We'll turn up the amplitude, and we'll actually look at the distortion over here on the scope. And we need to definitely turn this down. Got to first put the ground back on. Get that on a point here. So we're going to put the ground. I can't see somehow I have the reticule turned off on my scope. Oh, I can see it up here. Okay. All right, so this is going to be ground down here. So we're going to turn this back on DC coupled. And we are at 100 volts per division. And let's try this for now. Turn this up and see if I can get my scope to trigger. Okay, so let me tell you what's going on here. Alright, so this is our bias voltage here. You can see down here where it says RMS. This is at 227 volts. So this verifies our DC voltage at this point here at the plate. We measured it with just a regular voltmeter. Our scope is actually confirming that when I took the signal away. So now we're going to plug this back in, and you're going to see that the waveform, the AC waveform, rides up and down along this DC bias point. And what you're seeing now is the little bit of distortion you're hearing. Here, let's do it this way. Okay, that distortion you're hearing is, you can see that we're having a little bit of non-linearity going on in the top side, and we're seeing a little bit down on the bottom side as well. So run that, turn that back on. Now another thing we can do is, if we want to actually look at the AC waveform, we turn our scope back over to AC, and now we've taken out the DC component, which is at 200 volts, and we'll go ahead and put our ground point back up into the center of the screen, and then couple our scope back on AC. So now our AC waveform is going to vary around this point, because we've removed the DC component. And we'll fix our triggering. So we're triggered. Okay, so right now, this waveform, this thing down here says RMS is 133 volts, which is, that's pretty high, because our voltage per division down here is 300 volts. So we really got 1, 2, 3, about 3.5. It's about 350 volt swing in the output. So let's take a look at this down here. So this is, turn this off and slide this out of the way. So this load line, we're actually seeing a 350 volt swing across the plate, and that's been verified. So if we look at this thing here, this whole thing only goes up to 375 volts. So we're doing some real swing across this load line, almost a full excursion. Because if we, let's say that we're on this line, everything's fine, which we are. This one up here is going to be, this is 350, so this is about, I don't know, 390. So if you come back over here, we cross over here, and probably we're down here, I don't know, about 40. So we're actually doing full excursion on this load line. So what that's telling us is that we are getting out as much wattage as we can get with this particular load. Now, if we were to change this, we might be able to get a little more voltage out of it. If we change the screen voltage, which is going to move this whole set of curves down, right? Well, we won't do that today. We'll just stick with what we got here. The other thing we can actually play with today is we can move this bias point up and down. Well, not up. We certainly don't want to go up, because then we'll be swinging over into, we'll do some power dissipation over here. And technically you can do that if you were to, but you don't want the bias point. Like right now, with no signal in here, we don't want the bias point to sit on this side, because then we're actually could potentially destroy the plate. So if we did turn this down, that effectively moves us down in this curve here, and we won't get as much output swing out. But now the question is, if we had this speaker in a box, in an enclosure, would that be pretty loud? Yeah, I suspect it would be pretty loud. I mean, let's turn this up again. Let's put this back on run. And what? We don't have our DC voltage on. Okay, I can tell you that that's pretty loud. It's probably actually distorted in the audio playback here. I think the point of the meeting, the video today, was to take some measurements here, play around at the bench, and find out if this tube here, which is the 6SJ7, I have a bunch of these RCA metal cans, if they're capable of driving a little speaker like this, and the answer to that is yes. The other thing we learned about this is that we need, let's look at one more thing before we go. Let's look at the input voltage we need to drive the output at that level. that's going to be the waveform amplitude. And we're going to need that so that when we design our preamp, we're going to need to know what the output tube requires from a voltage perspective. All right. So we're going to hook up over here. This is our this is the input stage here, the voltage here, and we're going to turn on channel 2 on our scope. And in order to get that level of distortion, we'll turn this up. Okay, we're seeing here on our one waveform is we need 5 volts. That's what we're on peak to peak. We need 15 volts to get this level of distortion. We're on the 5-volt scale on the blue wire on the blue trace, so we need 15 volts. That's the peak to peak over here. You might not be able to see that. Let me see here if we can see that or not. Yeah, you probably can't see that number down there, but it's 15 volts peak to peak, which also confirms our theoretical result out of the simulation, because this line up here is 0, and we counted down, and this bottom line down here is about 15. So when we design our preamp circuit, we need to make sure that in order to get that level of distortion on the output, we need 15 volts. Okay, I think that's it for today.